Hey everybody, we're going to do a little bit of a function review. This is really a review for sort of an algebra review for our calculus class. So I want to talk a little bit about functions. A function, there's a lot of ways you can understand a function, and I'm going to give you just a very visual way, and that's think of a function as a machine. So here's my machine. Let's call it my F machine. I'm not going to name the machine. I throw in a number. Let's say I throw in a 1 and it spits out a 2. I throw in a 5 and it spits out a 10. I throw in a -7 and it spits out a -14. Now, some of you may have kind of guessed just by what's happening here. It's hard that this function is well, uh, this function is a 2x function, meaning I throw in x and it spits out 2x. So 5, 2 times 5 is 10. 2 times 1 is 2. 2 times -7 is -14. And that's a function. And sometimes, now, this function that I have here has a rule to it. The rule is that it doubles the number. By the way, the number that gets thrown in, is called the input. And the number that spits out is called the output. That's pretty easy to remember because in and out. The numbers that go in are the input, the numbers that come out are the output. So this function has a rule that it takes the input number and it doubles it. Now, it's not necessary for a function to have a rule. A function could be, in theory, a function could be random. Throw in a 27 and it spits out a -4. I throw in a 36 and it spits out I don't know, square root of 17. I throw in a 1 and it spits out a 29. So this function, I'm going to call it the R function for random. I don't know, random, but I'm saying that there may not be a clear rule like this function, maybe no rule. In theory, a function just has to have inputs that lead to outputs. As long as I input numbers and output numbers, and there is one cardinal rule of functions. There's one rule that functions can never violate, and here's what it is. You cannot have. Well, let me show you what's okay first. This is okay. I have a function here. I throw in a 5, and it spits out 1. I throw in a 2, and it spits out a 1. I throw in a -13, and it spits out a 1. Well, that's okay. In other words, I have different inputs, which all lead me to the same output. That's okay. In fact, this could just be the one function. In other words, this could be the function f of x equals 1. This function here would be f of x equals 2x. This one, I don't have any kind of rule for it, so I'm just going to leave that blank. But that's fine. You can have many inputs coming into one output. That's okay. Let me tell you what's not okay. So this is not okay, and do not try this at home. I am a trained professional. This is not okay. If I have a function and I throw in a 3 and it spits out a 5, and then later I throw in a 3 again. This time it spits out a 7. Now that is not okay. Because the best way that makes the most sense to me is that when I have this function machine, I have to know what's going to come out of it before I put the thing in. Think of it like we're talking about a machine. A machine is manufactured. A manufacturer. Some manufacturer makes stuff, I put something into the machine. I got to know what's going to come out of the machine. How could I? Otherwise, I can't function. I do that function. You see what I'm saying? I have to know that when I throw in this bolt, it's going to give me some nut, and that this piece is going to do that thing. I have to know that when I put in these, I got to know what's going to come out. Here, I don't know. This is, now it's still what we call in math a relation. It's still a relation, because the relation is just inputs and outputs. No, it's still a relation, but I guess you could say it's a dysfunctional relation. See what I did there? Um, so so that's the now what's an example? I want to give you an example of a relation. It's not, which is not a function, but it's pretty important. And that relation would be f of x to the x squared equals x. So put in it's out one because one squared equals one. But here I put it's out a because negative one. That's because negative one squared is one. That's f of one squared equals one. F of x squared equals x. I throw in a 9, so it can spit out a 3 because 3 squared equals 5. If I throw in a 9, it can also spit out a negative 3 because negative 3 squared also equals 9. So this is something that is definitely a relation. It's not random like this guy here. But it's, you know, but it's not technically officially, that's what I'm trying to say. It's not technically officially a function. And that's all, and but it's still called what we call a relation. So you have a relation that's just random. Now, by the way, many of you vertical. A function that fails the vertical, see, if I have a graph that's on the x y plane, but I actually want to, so that's x equals 3, x equals 9, and 3, x is 9, and y is 3, or it could be negative 3. This guy over here, see, the input is always the x value, by the way. So that's a good thing to know. Generally, the input is the x value, and the output is generally the y value. So this means that I have the input was 3 and the output was 7. So this one here, which goes from 3 to 7, tells me that the input was 3, the output was 7. But the second one tells me that the input was 3 and the output was 5. So by the way, I could also write a function by listing the individual points. I could write 3, comma 5. Then you have an input of 3, gives you an output of 5. Or I could have 3 and 3, comma 7. Here, when I list all the individual points, because there are two same x values, so different y values associated with them. that makes it not a function. It's not functional, and it would actually fail the vertical line test as you can see right there. And this, of course, failed, and the sideways parabola, of course, fails the vertical line test in many, many places. So that's a little bit about general functions. I want to, I just have to change the sheet of paper, and I'm going to show you something. Let's say you have two functions, right? We got two machines. For example, let's say we have the doubling machine, and then I throw in a one, and it spits out a two. I throw in a -5, and it spits out a -10. Let's say right down here we have a different machine. You have the squaring machine. So this two, which just got spit out of the first machine, falls into this second machine, and it gets squared. It becomes a 4. And the -10 comes in, and it becomes 100. So this is actually called, when you have the output of one function goes into the second function, this is actually called a composite function. Now, I'm mentioning this a lot because composite functions are definitely going to come up in calculus. And a lot of times, by the way, a lot of times people visualize it a little differently. When they have the two different functions like this, they kind of visualize it. I'm not the best artist in the world. They kind of visualize it that so this is the x squared function, and the 2x function, they kind of like put it like in here. Kind of like put it like in here. That's a little 2x part. So the 2x. So I have my so the 2x function is kind of inside the x squared function. It's just it catches the numbers first. When I throw in a 3, it first lands in the 2x function and spits out a 6. And then the 6 continues its journey and spits out a 36. And if I throw in a negative a -7, so that comes into the first it gets into the 2x function, and it gets doubled. Then it continues on its merry way, and it spits out, it becomes 196. So it gets squared. Um, what I like about this, a lot of times functions kind of look this way, because this would really, if I was going to write this as a function notation, I would write it this way: I write f of x is equal to 2x squared. So it kind of, and we say that the 2x is the inner function and the squaring is the outer function. So that's kind of like the same thing here, because the 2x box is inside the big x squared box. So inner, outer, inner, outer. Well, we're going to get to a certain thing in calculus. I don't want to give away too much. Some we're going to get to a calculus um, called it's called chain rule, but it deals a lot with composite functions. This whole idea of the inner function, the outer function, it's a big concept. But it's good to understand this here and now. An interesting question that you might wonder: what happens if I switch? Does it matter if I switch the machines? Does the order matter? Let's try it. Suppose I had the x square machine first, and then that lands into the 2x machine, and it doesn't matter which way I draw it. Um, so let's take the same numbers. I put in 1, squares it to become a 1, then that 1 gets doubled, it becomes a 2. Well, right away we see a difference, because here the 1 became a 4, and here the 1 became a 2. Let's see what happens to -5. I take the -5, I square it, it becomes 25. Then the 25 becomes 50. So again, 50, the -5 got a 50, but here the -5 got 100. If I didn't know better, let's say 3. So I'll put 3 in here, and the 3 gets squared, becomes a 9. And then 9 gets doubled, becomes an 18. Let's see what happens over here. I put in a 3. The 3 gets doubled and turns into a 6. Then the 6 gets squared and turns into a 36. Look at that, the same thing. This here is double that, oops, oh, I didn't even get on the same page. This here is, oh, that's the worst thing. Oh, there we go. So so the 4 is double the 2, the 100 is double the 50, the 36 is double the 18. So it seems that when I take the same input this way, it comes out double what it was over here. And that's actually not a coincidence because let's look at it this way. Suppose I throw in x. I throw in an x into this function. It's going to spit out a 2x. Then the 2x is going to come in here, and it's going to spit out a 2x squared, which if I just, get rid of the parentheses, that's 4x squared. 4x squared. Whereas here, if I throw in an x, it spits out an x squared, and then that x squared falls in here and spits out a 2x squared. So that's 2x squared, and that's 4x squared. So it is exactly double. So in other words, what I'm trying to say, I guess the moral of the story here is that when you switch the order, you're going to get a different answer, but it's not totally randomly different. There is some connection between the two. Well, when we see functions, composite functions is quite a big thing, and we see that many times. Let's just look at some simple functions. So some simple functions that we have. Most of the functions that we're going to see in our calculus in our basic calculus class is really just power functions. So let's say polynomial functions. In other words, f of x is 2x squared plus 3x minus 7. That's a straightforward polynomial. And sometimes we see sometimes the power sometimes could even be, well, let's look at another function called I'm going to call it R. R is the so R of x is one polynomial over another polynomial. I use R for rational, so we call it a rational function. And again, this is should be kind of a review of what you did in algebra. And sometimes we have functions where it could be g of x equals x to the 1/2 power. That's also a function. So it's an exponent, but it's a fraction. The exponent is a fraction. And sometimes we get these cool. Here's a cool composite function, and I'll show what I mean. So we'll call it c of x, c for composite. Actually, usually, whatever. The square root of x squared plus 1. Now, what's going on here? If you notice, the x squared plus 1 is the inner function, and the square root, is the outer function. If I was going to draw a picture of this, I would have my first machine. My inner machine would be x squared plus 1, and that would be inside my other machine, which is a square root of x function. So I throw in, for example, I throw in a 1, and it spits out a 2 because 1 squared plus 1 is 2, and then the 2 goes through the square rooty thingy, and it becomes the square root of 2. And this is again a composite function. That's the inner, that's the outer. Another kind of function I should write these down. So this first one is a polynomial. This is called a rational function. This is just a power function. This is a rational function. And see here is just a nice little composite function. That's all I'm going to say, composite function. And there are other kind of functions that we'll see, for example, let's see, e of x equals 2 to the x power. So e of 3 is equal to 2 to the third power, which is equal to 8. That's a nice function that, we're going to see. And, these are, different famous functions. And a lot of functions, by the way, e is exponent. And it's actually, this is actually called in the business exponential. And we're going to have, we also will see what they called, again, this is just sort of a cavalcade of functions right now. Yeah, another kind of function we see is a log function. So f of x equals log of x. Now, if you remember from algebra, the log goes as of a base, but when there's no base, it's base 10. So f of x, so for example, f of 100 is equal to log 100, and log of 100, see the base, if there's no base, it means it's base 10. So 10 raised to what power gives you 100? The answer is the second power. Because logs, logs, if you think about it, it's kind of exponents backwards. In other words, over here, I took 2, I raised it to third power, and I asked you what the answer was. The answer was 8. Here, I can write it this way, and I can write the log of 8 base 2, and I'm saying, okay, my target number is 8. The base that I'm raising is 2. What exponent from 2 is going to give me 8? So the answer is 3. 2 to the third power equals 8. So it's kind of, so in other words, logs is like exponents, only instead of telling me the exponent, I have to tell you the answer. We tell you the answer, you have to tell me the exponent. This has been a lovely video. We're gonna stop this one here for now. And it's just good to get a little feel for functions, because functions is a big part of math in general, and it's certainly, it's going to be a big part of calculus. So I'm going to end this now, and we'll see you guys next time. Bye.